This is a demo of how to set up the Excel spreadsheet for the strategic relocation problem that we discussed in session 22. The numbers in the yellow cells are the parameters of our problem. Okay. In column C, D, E, F, and G are the 5 possible locations for the service center: London, Madrid, Paris, Hamburg, and Rome. We also have in row number 2 the annual cost of operating the service center in each of these 5 locations. Then in the 5 by 5 arrays, we have the shipping time from each of the 5 service center locations to each of the 5 countries that are served by TRD, which are England, Germany, Switzerland, Italy, and France. And in column A, we have the share of the customers in each of these 5 countries. And in column J, we have other constraints for this problem, which include the shipping time from the service center to each location cannot exceed 1.5 days, and the average system-wide shipping time cannot exceed 1.1 days. And also, we can open at most 3 service centers, and we must open at least 2. So the first thing we're going to do is to set up the decision variables. As we discussed in class, the first set of variables are the binary variables that indicate at each of the service location whether or not we're going to open a service center there. Okay? As we denoted in class, we're going to denote these variables by y1, y2, y3, y4, and y5. Okay? And these 5 binary variables represent which service center to open. And let me highlight these cells in green. Okay? And let it put in some placeholder. Let's suppose that we're going to open a service center in London, Madrid, and Paris. And let's say we don't open in Hamburg, we don't open in Rome. Okay, so some placeholder, and we're going to ask the solver to change these values to achieve our objective. Okay. So that's the first set of decision variables. Now we're going to have a second set of decision variables that determine how we service the demand in each of the countries. Okay, and we're going to have, as discussed in class, a total of 25 binary variables. We denote them by XCS, okay, which represent the fraction of the demand in country C that will be served by service center in location S. Okay. So we're going to denote those 25 binary variables by an array of 5 by 5. Okay, let me put that here. Let me put border. And let me copy down the countries and put that here. We label these. These are the fraction of the demand in each country served by each center, or XCS. Let me format this. Also, and let me put in some placeholder. Let us suppose that we're going to serve the demand in every country from the service center here in London. So let's put 1, 1, 1. And so let me copy this value. So this is a placeholder. Okay, so now we're going to compute an objective. The objective in this problem is to minimize the total operating cost. Okay, well, that's obtained by taking each of the variable y, s, and multiply by the cost of operating the service center at that location. Okay? And we're going to sum them up across all 5 service centers. So we can do that using a sum product command of y1 to y5 with the cost of operating each of the 5 service centers. Okay? So we're going to minimize this objective values. Now we have a bunch of constraints that we need to satisfy. Okay? The first constraint is the total demand constraint, which means that for each country, so that means for each row, say in England, the fraction of the demand in England served by all 5 locations, the sum of that, of these 5 cells that are highlighted, must be equal to 1. Okay? So in other words, we must serve the demand from the customers in England, okay, by one of the 5 service centers. So the sum of these cells, we're going to require that to be equal to 1. And the same for the other 4 countries. The second constraint here is that the average shipping time in each country must not exceed 1.5 days. So and the shipping time in each country, well, it's obtained, say, to compute the average shipping time to the customer in England, we will look at the fraction, okay, of the demand in England that is served by each of the 5 service centers, and we're going to weight that by the shipping time from each of the 5 service centers to the England, okay, which is given by this particular row here. So we're going to have the sum product of the shipping time from each of the 5 service centers to England with the fraction of the demand from England served by each of the 5 service centers. And of course, we can then copy and paste, double click on the right hand column to copy the formula down. And then we have also a requirement that the system-wide shipping time, this will be system-wide shipping time. Well, we're going to take the shipping time in each of the 5 countries, which is computed here in the 5 highlighted cell, and you're going to weight that by the fractions of customers in each of those countries, which is given in column A. Okay, so we're going to do that using the sum product command, and we're going to require that this quantity here is less than the requirement of 1.1 days for the total system. And clearly this is not a feasible solution here, so we're going to have to solver to search for other solutions. And we're going to ensure that the total number of centers that we open is at most 3 and is at least 2. So we're going to have a cell which compute the number of centers open, which again can be something as simple as the sum of all the y's. Okay, so we're now ready to enter all of the constraints. So we're going to go in Data, Solver. So our objective is going to be B19, which is the annual operating cost, which we want to minimize. And we're going to do that by changing our decision variables, which are highlighted in green here. Now we're going to enter the constraints. The first constraint, as indicated in the slide, is that the total demand of each country served by the service center must be equal to 1. So all of these 5 cells must be exactly equal to 1. Each one of those must be exactly equal to 1. And the shipping time to each of the 5 markets or 5 countries must not exceed the requirement of 1.5 days. And the system-wide shipping time, which is this cell, must not exceed the requirement of 1.1 days. And the number of service center open must be no more than 3, which is given by this constraint. And the number of center open must be at least 2. And we have here that we have what we discussed in class, what we call a logical constraints, which mean that you cannot service from a center that is not open. And what we represent that service constraint as XCS must be less than or equal to YS. So in other words, if a particular Y is equal to 0, so we choose not to open that service center, then we cannot serve any country from that service center that is closed, that is not open. Okay? So we can represent that here as 5 separate constraints as follows. So all of the cell here, okay, in column C must be less than or equal to, let's say, Y1. Okay. Similarly, all the cell here that's under service center 2, Madrid, must be less than or equal to Y2. Okay. And similarly for here. And again, all the service to each of the 5 country from location number 4, Hamburg, must be less than or equal to Y4. Okay. And similarly, all the demand served by service center number 5, or Rome, must be less than or equal to Y5. Okay. And the last and final constraints that we have here is that all of our decision variables are binary. And Excel has a built-in functionality for that, which is called bin. So it automatically tells us that each of these variables must be 0 or 1. So we don't need this because the binary constraints capture that. You can choose simplex LP. And let's go to option. Okay, so we're going to make sure this box, ignore integer constraint, is unchecked. And we set our integer optimality to be some really, really small number to ensure that we get near optimal solution, okay, as close to optimal as we can. And that's it. So let's solve. And that's the answer.